June 2024. The Standard Model of Particle Physics, our most successful theory, describes 12 fundamental particles that make up all matter. Yet, it offers no fundamental reason for these particles possess their specific, wildly disparate masses. From the electron's whisper light 0.511 MeV to the top quark's colossal 173 GeV, these values appear almost arbitrary. To put that into perspective, if the electron were a single grain of sand, the top quark would be a 40-ton boulder. They are both fundamental, indivisible points of reality, yet their inertia, their very substance, differs by a factor of over 300,000. For decades, this chasm was a dark corner in the otherwise brilliantly lit cathedral of modern physics. We had the blueprint of reality, but the most fundamental numbers in it were written in an ink we couldn't read. The discovery of the Higgs boson in 2012 at CERN's Large Hadron Collider was a watershed moment, earning a Nobel Prize and seemingly completing the Standard Model. The Higgs field permeates all of space, a kind of cosmic molasses. As particles move through it, they interact with it, and this interaction, this drag, is what we perceive as mass. A particle that interacts strongly, like the top quark, becomes heavy. A particle that barely interacts, like the electron, remains light. And a particle that doesn't interact at all, like the photon, remains massless, forever traveling at the cosmic speed limit. This was a triumph. It gave us the cause of mass. But it left the deeper mystery untouched. The Standard Model can't predict the strength of these interactions, the so-called Yukawa couplings. We have to measure them experimentally and plug them into the equations by hand. It's like finding a divine recipe for the universe that calls for a pinch of electron mass and a mountain of top quark mass, without explaining where those ingredients come from or why those specific amounts are required. This is the heart of the flavor problem. The 12 fundamental matter particles, the fermions, are organized into 3 distinct generations or families. The first generation contains the up quark, the down quark, the electron, and the electron neutrino. These 4 particles build every atom in the universe, everything you can see and touch. But for reasons unknown, nature created 2 more generations, each a near-perfect but much heavier replica of the first. The second generation has the charm quark, the strange quark, the muon, and the muon neutrino. The third has the top quark, the bottom quark, the tau, and the tau neutrino. Why this triplication? Why does nature need these heavier, unstable cousins that existed for only a fleeting moment after the Big Bang, before decaying into the familiar particles of the first generation? It's a profound, seemingly unnecessary redundancy that screams of a deeper hidden pattern. The flavor problem isn't just one question, it's a cascade of them. Why 3 generations? Why the bizarre hierarchy of masses within and between them? Why are the neutrinos so fantastically light compared to everything else? The Standard Model is silent. It provides a list of ingredients, but no cookbook. And these are not just academic questions. The specific values of these masses are the most profound example of cosmic fine-tuning we have ever encountered. They are the dials on the control panel of reality, and their settings are terrifyingly precise. Consider the delicate balance between the up and down quarks. The down quark is just slightly heavier than the up quark. This tiny difference makes the neutron slightly heavier than the proton, allowing a free neutron to decay into a proton, an electron, and an antineutrino. But if the up quark were just a fraction heavier than the down quark, the protons would be unstable. It would decay, hydrogen atoms would vanish, stars would never ignite. The entire periodic table, the basis of all chemistry and all life, would be impossible. The universe would be a cold, dark soup of neutrons and radiation. Our existence hinges on a mass difference of less than 1%. The electron's mass is just as critical. Its value in relation to the strength of the electromagnetic force determines the size of atoms. If it were significantly heavier, atoms would be smaller, and the nuclear force might pull electrons into the nucleus, causing atoms to collapse. If it were lighter, atoms would be larger and more diffuse, perhaps preventing the stable chemical bonds needed for complex molecules like DNA. Even the ghostly neutrino, once thought to be massless, plays a crucial role. Data from experiments like Japan's Super Kamiokande and Canada's Sudbury Neutrino Observatory revealed that neutrinos oscillate, changing flavor as they travel, a phenomenon only possible if they possess mass. While their mass is minuscule, their sheer abundance means they collectively influence the gravitational landscape of the cosmos, shaping the formation of galaxies and cosmic structures. Change their mass, and the cosmic web we see in deep field surveys might look entirely different or not exist at all. Our universe, our very existence, is balanced on the knife edge of these 12 numbers. Are these just cosmic coincidences, a series of unbelievably lucky rolls of the dice? Or are they the fractured evidence of a deeper, more elegant, and currently broken symmetry? From that paradox of cosmic coincidence emerges an even deeper tension, a structural flaw so profound it has been called the greatest crisis in fundamental physics, the hierarchy problem. If the seemingly random masses of the 12 fermions are a crack in the Standard Model, the hierarchy problem is a gaping chasm. It concerns the mass of the Higgs boson itself. At around 125 GeV, the Higgs is surprisingly light. The problem arises when we consider the highest energy scale known to physics, the Planck scale, around 10 to the 19 GeV. This is the energy at which gravity becomes as strong as the other forces, where spacetime itself is expected to dissolve into a quantum foam spacetime, and our current theories break down. In the world of quantum mechanics, a particle's bare mass is constantly being modified by a cloud of virtual particles that flicker in and out of existence around it. These quantum corrections should naturally drag the Higgs boson's mass all the way up to the Planck scale. For the Higgs to remain so light is like trying to balance a pencil on its tip for 14 billion years. Any tiny quantum nudge should have sent it soaring to this astronomical value. The fact that it hasn't implies that there is some unknown physics, some exquisite cancellation mechanism that is protecting it. This discrepancy, this unnatural fine-tuning, alongside the flavor problem, signals a fundamental glitch in our understanding. It tells us the Standard Model is not the final word. It is an incomplete, low-energy approximation of a much grander theory. And it is in the search for this grander theory that physicists hope to solve both the hierarchy and the flavor problems at once. The prevailing theories beyond the Standard Model are not just minor adjustments, they are radical reimaginations of reality. The most elegant of these is supersymmetry, or SUSY. It proposes a profound new symmetry between the two fundamental classes of particles, fermions and bosons. For every fermion, there is a corresponding boson superpartner, and for every boson, a fermion superpartner. This doubling of the particle zoo provides the perfect cancellation mechanism. The quantum corrections from the known particles that try to drive the Higgs mass up are perfectly balanced by corrections from their superpartners, stabilizing its mass naturally. SUSY was the leading contender for decades, but despite years of searching with the LHC's ATLAS and CMS detectors, not a single superpartner has been found. This doesn't kill the theory, but it forces it into more complex and less natural-feeling configurations. Another approach is to seek unity at higher energies. Grand unified theories, or GUTS, propose that in the searing heat of the first moments after the Big Bang, the electromagnetic, weak, and strong nuclear forces were all merged into a single unified superforce. The universe existed in a state of perfect, elegant symmetry. As the universe expanded and cooled, this grand symmetry broke, shattering into the distinct forces we see today. In this violent process, particles like the Higgs acquired their properties, and the fermion masses were set. In such a framework, the seemingly random mass ratios are no longer random at all. They are the predictable, calculable fragments of that original unified structure, like the different lengths of crystal shards that break from a single symmetrical geode. A third, even more exotic idea is that the hierarchy problem is an illusion created by our limited perception of spacetime. Theories of extra dimensions, like the Randall-Sundrum model, posit that our 3D universe is just a brane floating in a higher dimensional space called the bulk. In this scenario, gravity is not fundamentally weak. It just appears weak to us because, unlike the other forces which are trapped on our brain, gravity can leak out into the extra dimensions. This elegantly explains why the Planck scale is so high and the Higgs mass so low, without any fine-tuning. These theories, SUSY, guts, extra dimensions, are all attempts to explain how a pristine higher symmetry was broken and how that breaking event gave birth to the specific glitched numbers that define our world. And here is the final mind-altering consequence. That breaking of symmetry, the event that bestowed mass upon the fundamental particles, did more than just set the cosmic constants. It fundamentally altered the nature of time. Mass is inertia. It is the resistance to a change in motion. According to Einstein's special relativity, a massless particle, like a photon, has no choice but to travel at the speed of light. From its own perspective, it experiences no time. Its journey from a distant star to your eye is instantaneous. It is born and absorbed in the same moment. It has a path through space, but no story in time. By acquiring mass, a particle is forced to slow down. It is forever forbidden from reaching the speed of light. This act of slowing down is what gives it a trajectory. It carves a world line, a path with a distinct past, a present, and a future. It acquires a biography. Our mass, then, this fundamental property we owe to a cosmic glitch, is the very anchor that tethers us to this reality. It is the consequence of the universe's broken symmetries, trapping us in the relentless forward march of time. The glitch is not a flaw, it is the very condition of our existence.